chromium nucleus. The electronic configuration of chromium shows the electronic configuration as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d5. So this 4s1 subshell is now becomes half filled. Now becomes half filled, and the last subshell, that is 3d, becomes again half filled with 5 electrons. This is called 3d. The maximum capacity of this subshell is of 10 electrons, but 5 electrons are present here, hence it is half filled. And whenever the last subshell is half filled, and last but one also becomes half filled. So last and last but one subshells are whenever half filled, that particular electronic configuration gives maximum stability to the respective element or respective nucleus. Hence the observed electronic configuration of chromium becomes, or chromium shows this type of electronic configuration, that is last 4s and 3d subshells are half filled, containing 1 and 5 electrons respectively. So this is all about chromium. Then after 25th, that is magnesium, and 26th, that is iron, 26 and 25. So these two elements shows a normal electronic configuration, that is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. This is common. 2 plus 2, 4, 4 plus 6, 10, 10 plus 10, 20 plus 20, 20 plus 5. That is 3d5 will be the electronic configuration of manganese with atomic number 25. Similarly, the electronic configuration of iron can be written as with 26 atomic number, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d6. 6 plus 2, 8, plus 8, 16, plus 6, 22, plus 4, 26 will be the electronic configuration of manganese and iron. This is very simple. Now the next element is cobalt with atomic number 27 and nickel atomic number 28. So these electronic configurations can be written as 7 and 8 last subshell 3d, that is 2 plus 2, 4 plus 6, 10 plus 10, 20 plus 7, 27 atomic number is equal to 27. Similarly, the electronic configuration, this is the electronic configuration of cobalt, and this is nothing but the electronic configuration of nickel with atomic number 28, and this summation gives the number of electrons is equal to 28. Hence, it is 100% correct electronic configuration on the basis of above principle with one by one step or with energy levels with increasing energy. So this is all about cobalt and nickel. Now 29th member is nothing but copper. Copper atomic number 29. So copper atomic number 29 shows again abnormal electronic configuration, that is like chromium. Chromium, out of these 30 elements, chromium and copper gives two different types of electronic configurations, that is expected electronic configuration, that is on the basis of above principle, and observed electronic configuration while taking part in a chemical reaction. So the above, on the basis of above principle, the normal electronic configuration of copper can be written as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d9. That is the expected electronic configuration. But in actual practice, while taking part in a chemical reaction, in order to give the stability to the nucleus of copper, copper shows different electronic configuration, that is called observed electronic configuration, and that is equal to 1s2, 2s2, 2p6, 3s2, 3p6. Look, these two, that is last and last but one sub-energy level, that is electron moves from 4s sub-energy level towards the 3d sub-energy level, or 4s orbital to 3d orbital. So due to transfer or shifting of a single electron from 4s to 3d, one electron is added. In case of 3d, it becomes 3d10, and one becomes short in case of 4s, and hence it becomes 4s1. So 4s1 becomes half filled, and 3d10 becomes completely filled. So whenever, as we mentioned before, in case of chromium, whenever last two subshells, that is last but one, and the last subshell, that is 4s and 3d, both are half filled, at that time electronic configuration or the stability to the nucleus of chromium is observed. In case of copper, the same case happen, that is the last subshell is completely filled with 10 electrons, and last but one subshell is half filled with 1 electron. Hence, whenever last subshell is completely filled and last but one subshell is half filled, at that time such type of electronic configuration is called observed electronic configuration, shown by copper in while taking part in a chemical reaction. Hence it is most stable electronic configuration of copper. Hence in case of first 30 elements, only copper and chromium, or chromium atomic number 24 and at copper atomic number 29, shows different electronic configurations, abnormal electronic behavior or electronic configurations expected and observed. So this is all about electronic configuration of copper. And the last element, that is called zinc. Only single electron is added in case of 3d subshell. So the electronic configuration of zinc with atomic number 30 becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d10. So on the basis of above principle, it is very easy to write, or it is very easy to draw the correct electronic configurations, 100% correct electronic configurations of any element in the periodic table. And this is all about above principle, that is building up or a distribution which gives an idea about the distribution of electrons in the sub-energy level, that is S, P, D and F, on the basis with increasing energy on the basis of above principle. So this is all about above principle and all the articles in case of atomic structure or structure of an atom. Thank you. So in yesterday's lecture, we discussed the discussion about Hund's rule of maximum multiplicity is over. So this, the final and the last part of this particular above principle, that is some characteristics of above principles are considered or explained by me in yesterday's lecture. That is filling of electron takes place in sub-energy levels, that is orbitals, in accordance of increasing energy level. This is the base of Bohr principle. Filling of electrons in the sub-energy levels, that is the respective orbitals, takes place on the basis of increasing energy of the orbitals or increasing energy of the sub-energy levels. To introduce or to give the electronic configuration on the basis of Bohr principle, we know that Bohr means building up. To explain the electronic configurations of first 30 elements, that is from hydrogen to zinc. Zinc has atomic number 30, while hydrogen is the first element in the periodic table. So this for Bohr principle, that is, in order to give the electronic configuration of the elements, n plus 1 energy rule is used. We discuss about this n plus 1 rule on the basis of Bohr principle, that is, filling of electrons in incompletely filled S, P, D and F sub-energy levels takes place with increasing energy. This is the principle called as Bohr principle. Initially, Pauli's exclusion principle gives the filling of electrons in the S sub-energy level, and filling of electrons in S sub-energy levels has no much more importance as compared to distribution or filling of electrons in the incompletely filled P, D and F orbitals, because S subshell has a capacity to accommodate maximum 2 electrons. So as S subshell contains or has a capacity to accommodate or to occupy maximum number of electrons is equal to 2 in number, it means that it has only one, that is a single orbital, and called S orbital, that is 1s, 2s, 3s, 4s, 5s, 7s, 6s and 7s respectively. But the capacity of P, D and F subshell is different than that of S sub-energy level, because P sub-energy level has a capacity to accommodate 6 electrons, or in simple words, P sub-energy level contains 3 orbitals, and that's why it has a capacity to accommodate, or a P sub-energy level contains 3 orbitals, that is called Px, Py and Pz. Each contains 2 electrons. It means P sub-energy level occupy or accommodate maximum number of electrons is equal to 6 in number. So this is all about the P subshell. Similarly, D subshell has a capacity to accommodate a maximum number of electrons is equal to 10 in a number. So maximum 10 electrons are occupied or accommodate in the D sub-energy level. Hence the distribution of electrons in the D sub-energy level is also have a much more importance than Pauli's exclusion principle, that is distribution in S sub-energy level. And finally, F sub-energy level contains 14 electrons. Each orbital contains maximum 2 electrons. As there are 7 orbitals on the basis of magnetic quantum number, 7 orbitals, each orbital contains 2 electrons. It means 7 multiplied by 2 is equal to 14. This is the capacity or a maximum capacity to accommodate electrons in case of F sub-energy level. So P, D and F sub-energy level contains 6, 10 and 14 electrons respectively. And initially, on the basis of Pauli's exclusion principle, we can say that S sub-energy level contains maximum 2 electrons with a single orbital. So on the basis of Pauli's exclusion principle and Hund's rule of maximum multiplicity, distribution of S and distribution of distribution of electrons in P, D and F subshells takes place. But this Pauli's exclusion principles also nullify or also overweight the difficulties in Pauli's exclusion principle and Hund's rule of maximum multiplicity. So on the basis of Pauli's above principle, we can add, we can distribute, we can fill these incoming electrons in the sub-energy level or orbitals, respective orbitals with increasing energy. This is the base of above principle, that is called building up electronic configurations of the elements. So on the basis of above principle, we can draw or we can write electronic configuration on the basis of above principle and orbital wise electronic configuration on the basis of above principle. Very simple, on the basis of above principle. So these are the sub energy levels: 1s, 2s, 3s, 4s, 5s, 6s and 7s. Similarly, p subshells, that is begins from 2p to 7p, that is 2p, 3p, 4p, 5p, 6p and 7p. Similarly, 3D, 4D, 5D, 6D and 7D. And lastly, 4F, 5F, 6F and 7F. These are the sub-energy levels in case of above principle, that is SP, D and F, which are used to draw or which are used to determine the electronic configuration of elements in the periodic table. We can write electronic 118 elements in the periodic table, that is electronic configuration of 118 elements in the periodic table. So the begins with atomic number and symbol of atomic number and the electronic configuration of the elements on the basis of above principle. We know that S, P, D and F subshells contains maximum 2, 6, 10 and 14 electrons respectively. The maximum capacity to accommodate number of electrons in S, P, D and F elements is of 2, 6, 14 and 2, 6, 10 and 14 electrons respectively. So each sub-energy level, that is S, P, D and F, fill these electrons 2, 6, 10 and 14 electrons in these S, P, D and F subshell. It is very easy to draw, or it is very easy to write the electronic configurations of all the 118 elements in the periodic table. That is, hydrogen is the first element in the periodic table. So hydrogen has an atomic number is equal to 1. So it means that hydrogen has a 1 proton. It means there is a 1 electron around the nucleus in K main shell. So add first electron in the 1s sub-energy level or s orbital. So electronic configuration of hydrogen becomes 1s1. This is the simple thing about the electronic configuration of hydrogen, which is the simplest form, that is 1 electron, atomic number 1, number of electrons is equal to 1. Electronic configuration is 1s1. Now this S subshell also has a capacity of 1 electron. So second electron is added in the same 1s sub-energy level or s orbital, that is 1s2 will be the electronic configuration of helium, which has an atomic number 2 and it is the second member of the periodic table. So this is all about 1s1 and 1s2 in case of hydrogen and helium. Now the capacity of 1s is fully, or it is completely filled. Therefore electron moves from 1s to again 2s subshell, that is 2s. So it has also a capacity of 2 electrons. So the lithium having atomic number is equal to 3. First 2 electrons are present in 1s. Therefore, 1s2 will be the common electronic configuration of lithium. It has a 3 atomic number 3 electrons, hence a 2s subshell. 2s subshell contains only 1 electron, hence the electronic configuration of lithium having number of electrons is equal to 3 is 1s2 2s1, that is 2 plus 1 is equal to 3. This is the electronic configuration of lithium. Again, this 2s subshell has a capacity to accommodate 1 electron. So the fourth element is nothing but beryllium, having atomic number is equal to 4, number of electrons is equal to 4. 2s has a capacity to accommodate 1 electron again. Therefore, 1s2 and 2s2 will be the electronic configuration of beryllium. That is 2 plus 2, that is equal to 3, that is equal to 4. 1s2, 2s2 will be the electronic configuration of beryllium. 1s2, 2s2. Now the capacity of these two subshells, that is 1s and 2s orbitals, is completely filled or totally filled. Therefore, electron moves from 2s to 2p subshell, that is p subshell, 2p subshell. Now this 2p subshell has a capacity to accommodate number of electrons is equal to 6. So 6 electrons are added in this 2p subshell. Hence the electronic configuration of 5 atomic number 5, 6, 7, 8, 9 and 10 can be written very easily in this following fashion, that is carbon in त्यानंतर 5 boron 6 carbon नाइट्रोजन 7 ऑक्सीजन 8 9 आणि निऑन 10. One is 2. So the boron is the 5th element in the periodic table, carbon is the 6th, nitrogen 7, oxygen atomic number 8, fluorine atomic number 9, and this is an inert gas having atomic number is equal to 10. So 1s2, 2s2 will be the electronic configuration of beryllium, and now the 5th element is boron. Therefore 1s2, 2s2 1s2, 2s2 is the common electronic configuration of boron for the first 4 electrons. But atomic number of boron is 5. It means it contains 5 electrons. So 2 plus 2, that is 4. Then electron moves in p subshell, that is 2p1 will be the electronic configuration of boron. So 1s2, 2s2, 2p1 will be the electronic configuration of boron. Now again 5 electrons are added. 5 electrons are added in 2p subshell. Therefore 6th electron, that is 1s2, 2s2, 2p2 will be the electronic configuration of carbon. Now again 4 electrons are added. So 1s2, 2s2, 2p3 will be the electronic configuration of nitrogen. It is correct because 3 plus 2 is equal to 5, 5 plus 2 is equal to 7, 7 electrons are present in case of nitrogen. Similarly, again 3 electrons are added. So 1s2, 2s2, 2p4 will be the electronic configuration of oxygen. 1s2, 2s2, 2p5 will be the electronic configuration of fluorine. Now check the electronic configuration of fluorine. Is it 100% correct? Because 1s2 means K 2 electrons. And the second main energy level contains 5 plus 2, that is 7. So 2 plus 7 is equal to 9, and this is the atomic number of fluorine. And the element which contains number of electrons is equal to 7 in the outermost or valency shell, it is called an halogen, and fluorine is the first halogen in the periodic table. And now the 10th element, that is neon. Neon is an inert gas. An inert gas has a characteristic, that is the completion of octet. 6 plus 2, that is equal to 8. And these 8 electrons are present in the L main energy level, and first 2 are present in K. So 2 plus 8, that is equal to 10. 10 will be the atomic number of neon, and neon is the first inert gas in the 0 group in the periodic table. So 8 electrons are present, and it is chemically inert, or it is called inert gas, or it is also called a noble gas element. So this is all about first 10 atomic numbers and elements with electronic configuration. Now from sodium, that is atomic number 11. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and sulfur. This is 11, this is 12, 13, 14, 15, 16. Six, and 6. So sodium having atomic number 11, magnesium 12, aluminium 13, silicon 14, phosphorus 15, and sulfur 16. So first 3 subshell, that is 1s2, 2s2, and 2p6, that is 6 plus 2, 8 plus 2, 10. 10 will be the atomic number of neon. And now 2 plus 2 is equal to 4, 4 plus 6 is equal to 10. Now electron moves forward, that is towards the 3s subshell or s sub energy level. Therefore, in case of sodium, the electronic configuration of sodium can be written as 1s2, 2s2, 2p6, and 3s1. Now add 2 plus 2 is equal to 4, 4 plus 6 is equal to 10, 10 plus 1, that is 11, and 11 will be the atomic number of sodium. Hence this is the correct electronic configuration of sodium. And due to last electron, which is unpaired, and it is present in the M subshell, only one electron is present in the valency shell of sodium. Hence sodium has this free or mobile electrons. Hence it is very reactive in nature, and it is due to its reactivity it is placed in the kerosene. Now the 12th element, that is magnesium. Again 1s2, 2s2, 2p6. S subshell has a capacity to accommodate again one electron. Hence the electronic configuration of magnesium becomes 1s2, 2s2, 2p6, 3s2. 2 plus 2, 4, 4 plus 2, 6, 6 plus 6, 12. 12 is the electronic configuration of magnesium. Now 3s2, 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 3s2. Aluminium 2 plus 2 plus 6, 10, 10 plus 2, 12. Now 3s has a maximum capacity to accommodate number of electrons is equal to 2 in number. Then electron moves towards the next sub-energy level, that is next subshell with higher energy, that is 3p. 6 electrons are added consecutively in this 3p subshell because it has a capacity to accommodate 6 electrons, and that will be the electronic configuration of 6 consecutive elements. So in case of aluminium, 3p1, 1s2, 2s2, 2p6, 3s2 and 3p1. 2 plus 2 is 4 plus 2 6 plus 6 12 plus 1 13. 13 will be the atomic number of aluminium. Similarly for silicon, electronic configuration can be written as 3p2. For phosphorus 3p3. For sulfur 3p4. For silicon 1s2, 2s2, 2p6, 3s2 will be the common, that is 12 plus 2 14. 14 will be the atomic number of silicon. For phosphorus 15 electrons are observed. 1s2, 2s2, 2p6, 3s2, 12 common plus 3, that is 12 plus 3 15, that is equal to 15 will be the electronic configuration of phosphorus. Similarly, the electronic configuration of sulfur can be written as 1s2, 2s2, 2p6, 3s2 and 3p4. 2 plus 2 4, 4 plus 4 8, 8 plus 2 10, 10 plus 6 16, that is equal to 16. So these are the electronic configurations of first 16 elements in the periodic table. Sulfur ನಂತರ ಕ್ಲೋರಿನ್ ಡೆವಲಪ್ ಕ್ಲೋರಿನ್ argon 18 potassium 19 calcium 20 scandium 21 titanium 22 3p6 3p, ether 6, ether 5, ether 6, ether 6, ether 6, ether 6. So the electronic configurations of next element, that is after 16, after sulfur, that is equal to 17. 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18. But chlorine has an atomic number is equal to 7. Only 5 electrons are added. 3p4 in case of sulfur, 3p5 in case of chlorine. The electronic configuration of chlorine becomes 1s2, 2s2, 2p6, 3s2 and 3p5. 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, that is equal to 12, 12 plus 5 equal to 17. So the distribution is like this. K is equal to 2, L is equal to 8, and this outer, that is M, outer or outermost shell M contains 7 electrons. So this element, that is chlorine, contains 7 electrons in the valency shell or outermost shell. Hence it becomes very reactive, or it is called halogen, which comes just below to fluorine. Fluorine is the first halogen with atomic number 9, that is 2, 7, and chlorine will be the second just below to fluorine in the halo group with atomic number 17, and distribution becomes 2, 8 and 7 in K, L and M respectively. Hence this electronic configuration becomes correct. 1s2, 2s2, 2p6, 3s2 and 3p5. One electron can be accommodated. There is a vacancy of one electron in 3p subshell. Hence, the electronic configuration of argon with atomic number 18, that is 2, 8, and 8. 2 plus 8, 10, 10 plus 8 is equal to 18. Hence, argon is 100% inert gas or noble gas. Hence, electronic configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6. 1s goes to K main shell, 2s2 and 2p6 goes to L main shell, and M, that is the valency shell of argon, contains 8 electrons. Hence, it is chemically inert, or it is called a noble gas or inert gas, and which comes just below to neon. Neon has atomic number 10, just below to neon. Plus add 8 electrons, that is 18, and 18 is nothing but the atomic number of argon. So this is all about electronic configurations of first 18 elements. Now, the capacity of 3p subshell is over, which is of 6 electrons. Now, in case of potassium, which has an atomic number is equal to 19, electron moves towards the next sub-energy level with higher energy, that is 3p to 4s, and this 4s has a capacity to accommodate only 2 electrons. So 4s1 will be the electronic configuration of potassium, and 4s2, this common, 4s2 will be the electronic configuration of calcium. 4s1 and 4s2, this is the electronic configuration of potassium is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18 plus 1, that is 19, and 19 will be the electronic, 19 will be the atomic number of potassium. Similarly, in 4s1, there is a one capacity to accommodate an electron. That's why the electronic configuration of calcium with atomic number 20 becomes 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. These are the electronic configurations of first 20 elements in the periodic table. Now, moving towards the capacity of 4s subshell is completely filled, or sufficient, or totally fulfilled 4s subshell with 2 electrons. Now electron moves towards the next energy, next orbital, or next sub-energy level with increasing energy, and we know that D subshell has a capacity to accommodate 10 electrons, hence it has a greater capacity of energy or a higher energy as compared to S and any S and P orbitals respectively. So the electronic configurations from atomic number 21 to 30, all the 10 electrons are added in case of 3D subshell. So the electronic configuration of the electronic configuration of scandium with atomic number is equal to 21. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. The 21st electron, 2 plus 2, 4, 10, 20. 3d1 will be the electronic configuration of scandium. 2 plus 2, that is 4, 4 plus 6, 10, 10 plus 10, 20 plus 1, that is 21 will be the electronic configuration of scandium. Next one, that is atomic number 22, titanium. Similarly, add again one electron, it becomes 3d2. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d2 will be the electronic configuration of titanium. Now 8 electrons are added in incoming elements. So the elements are written as follows. Davis, chromium, choice. So atomic number 23, that is called vanadium. 23 atomic number and electronic configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d3. The summation becomes 23. 2 plus 2, 4 plus 6, 10, 10 plus 2, 12, plus 6, 18, plus 2, 20, plus 3. 23 will be the electronic configuration of vanadium. Now, the electronic configuration of 24th element, that is called chromium. 24th element, that is called chromium, has some different ideas about to show the chemical and physical properties. So this chromium shows two types of electronic configuration. First type of electronic configuration is called expected electronic configuration. Expected electronic configuration. So the expected electronic configuration means electronic configuration on the basis of Bohr principle is called expected electronic configuration. No change in the filling or distribution of electrons in p, d and sp, d and f subshell, sp, d subshell. Hence the normal similar electronic configuration can be written above. The electronic configuration, that is expected electronic configuration of chromium, becomes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d4. So this 3d4 is the d subshell which is incompletely filled, and last but one subshell, that is 4s, is completely filled. So last but one subshell is completely filled and last subshell is incompletely filled. This is the electronic configuration which is called expected on the basis of Bohr principle. But in actual practice, while taking part in a chemical reaction, chromium shows different electronic configuration or ideas about different electronic configuration, and that's why in order to give stability